Deep beneath the Yellowstone Supervolcano, reservoirs filled with explosive magma suggest that future volcanic eruptions may be more likely in the northeast of the region. By studying the natural electromagnetic fields around the Yellowstone Caldera, scientists at the U.S. Geological Survey and Oregon State University have discovered at least 7 reservoirs with high magma content. Located at depths ranging from 4 to 47 kilometers around the point where the crust meets the mantle, some of these reservoirs appear to be interconnected and perhaps filling each other like intricate tunnels. The new findings suggest that volcanic activity on the western edge of Yellowstone may be waning. In certain parts of the caldera complex, the magma chambers are stored in separate regions with low melt fractions, meaning these areas are unlikely to erupt. Meanwhile, the researchers found a significant magma reservoir associated with explosive eruptions beneath the northeastern Yellowstone caldera. This northeastern reservoir of rhyolite melt storage is being filled by basalt rising from the Earth's lower crust, supplying it with heat and material. The Yellowstone caldera is one of the largest volcanic systems on Earth, having hosted 3 major caldera-forming eruptions in the past 2 million years, interspersed with periods of less explosive and smaller volume eruptions. Yellowstone's caldera-forming eruptions are fueled by rhyolite melts stored in the middle to upper crust. Seismic tomography studies indicate that a large region of rhyolite melt extends beneath the Yellowstone caldera. With melt volumes estimated to be 1 to 4 times greater than the eruption volumes of the largest past caldera-forming eruptions, and melt fractions estimated to be as high as 6%. Seismic velocities are strongly influenced by temperature, pressure, and melt. However, magnetotelluric data are particularly sensitive to the presence of melt, making them ideal for constraining volcanic systems. Here we use magnetotelluric data to model the resistivity structure of the crustal magma reservoir of the Yellowstone caldera and to constrain the potential of the region to generate major volcanic eruptions. We find that rhyolite melt is stored in a discrete region beneath the caldera with a low melt fraction, indicating that the reservoir is not eruptible. Typically, this region has melt volumes equivalent to small volume post-caldera Yellowstone eruptions. The largest rhyolite melt storage region, concentrated beneath the northeastern Yellowstone caldera, has a storage volume similar to the eruptive volume of the smallest caldera-forming eruption at Yellowstone. We identify a region of basalt migrating from the lower crust, merging with and supplying heat to the northeastern region of rhyolite melt storage. Based on our analysis, we suggest that the location of future rhyolite volcanism has shifted to the northeastern Yellowstone caldera. Volcanoes are triggered by geological forces that operate on long time scales, usually measured in thousands to millions of years. While there may be signs of magma movement or other volcanic activity, these processes are usually very slow compared to human timescales. Volcanic activity is notoriously difficult to predict, so never say never.